Okay, so my name's Mike Hayden, and I'm the project leader for 1.2, which is terahertz generation, detection, and spectroscopy. And as you heard from Alex, there's a number of wonderful materials gains that have been developed over the last 10 years. Most of them for telecommunications applications or displays or something like that, and high-speed networks. We started thinking, are there other applications that we can utilize these electro-optic materials for? And so that's really what this project is about. The generation and detection of terahertz radiation is mostly a collaboration between UMBC and the University of Washington, where they make the materials and we're doing the terahertz. And the spectroscopy is really an application of using terahertz systems in a different way to study some of the materials that are being made in the center, mostly in the other thrust, which has to do with organic photovoltaics. So I'll talk about both of those things, and that's really a collaboration between UMBC and Georgia Tech and UMBC and University of Washington. So since the terahertz probably isn't on everybody's the front of your minds, most of you maybe being chemists and other disciplines, we're going to have a little bit of vocabulary here. What is terahertz radiation? And this is radiation between the microwave and the visible, right? So we're stuck right in here in this region of the electromagnetic spectrum. And just to give you some template here, 1 terahertz in frequency is 300 microns in wavelength. And for wave numbers, that's 33 wave numbers. And notice also that the photon energy is 4 millielectron volts. So compare this with the photon energy of an X-ray. X-rays are used for diagnostics and imaging and things like this these days, right? And radiography and non-destructive testing. And the photon energy of X-rays is about 1 million times higher than they are for terahertz. The terahertz photons also do a good job of penetrating most materials, especially dielectrics, and are good for some very good applications like package inspection, food inspection, mail inspections, imaging in airports and things like that. And so that's sort of the overall driver here, is that the photon energy is very low, and so it's not ionizing and it's not damaging, but still has a good penetrating depth and good resolution. The problem is that it sits in this gap where, in this region, electronic processes give rise to generation and detection of photons, and it's a pretty easy process, right? And down here you have other kinds of molecular processes, but in between, the fundamental vibrations that are going on in the materials are collective modes. And that's a very difficult thing to generate, and so you have to be careful and you'll have to be very precise about how you go about it. So you can't do electronic and you can't do some of these rotational things, but you can do some nonlinear optical techniques to generate and detect terahertz radiation. And so to do that, we have to understand a few other terms: phase matching and coherence length in terahertz emitters and sensors. So for all nonlinear optical processes, usually there's some sort of phase matching that you have to worry about. And of course, the coherence length is also important. So for the terahertz application, we generally send an optical beam into the material, and as it travels through the material, it generates a terahertz beam. And if we want that to be very efficient, we want those beams to travel side by side so the energy can exchange with each other. And that's really what phase matching is all about. It so happens that in the electro-optic polymer systems, we have a sort of fortuitous situation, and that is that I'm plotting here the terahertz index of refraction versus the frequency in the terahertz regime. You notice that index is relatively flat for an EO polymer, and that's to be compared with typical inorganic or any kind of crystalline lattice materials that have this lattice resonance where the index is very different. And this gives rise to very poor phase matching, because this phase matching process is really one where we are matching the index of the terahertz wave in the polymer with the group index of the pump beam. Because we're using short pulses, we have to worry about the group index. And so we have to match those two. And that's pretty well done in polymer systems. And if they are matched, then this denominator is low and the coherence length is large. And then you can use thick materials to generate coherently this radiation. The next topic I'd like to have some discussion about is terahertz time domain spectroscopy. And this is basically spectroscopy like you're used to seeing it in terms of how you do it. The major difference is that we're doing coherent spectroscopy, which means not only do we get the amplitude change when we're making spectroscopy, but we're doing a measurement, we're also getting the phase information. So just a little diagram of that. You would send your terahertz pulse through your, say, substrate, and you have some reference. And then you send your terahertz pulse through your sample and the substrate. And notice that there's some reflections possibly, and that's a delay from this time. So that's a phase change. But then the amplitude is also changing. Because we have the phase and the amplitude in a coherent manner, we can extract the complete dielectric function of the material, of this material, both the real and imaginary parts of the index of refraction, or the real and imaginary parts of the photoconductivity if we're looking at semiconducting polymers or organic photovoltaics or something like that. And the last sort of vocabulary is optical pump terahertz probe spectroscopy. And this is what we're doing with organic photoconductors. Basically here we're creating some charge carriers by shining a visible light on the material. And once those charge carriers are created, we probe it with a very short terahertz pulse. Remember, the terahertz pulse is at frequencies that are very similar to the electron relaxation times and the recombination times in these materials. So it's very sensitive to the charge carriers. And that process is similar to what I showed you before. We look at what happens when the terahertz pulse goes through the material, and we call this the unexcited state. And then we excite the material, create some charge carriers, and send a terahertz pulse through, and get two different traces. If you subtract those two, you would get this. You can actually get this one directly if you modulate the pump beam. And this thing here is directly proportional to the amount of photoconductivity, and we get the real and imaginary part from this coherent detection. If you model this then, you can extract things like carrier mobilities, charge concentrations, and efficiencies. And this hopefully will be of some value to people who are making new materials in this area. So just to sort of recap and finish up, the two projects that we're working on really are generating wideband terahertz detection and generating wideband terahertz generation and detection. And there'll be a poster on this tomorrow, so I won't go into any of these details. And this kind of process of looking at charge generation and its dynamics in these kind of organic photovoltaic materials. And this little cartoon shows what we think is going on here is that you excite the material, you create some electron hole pairs, and then something could happen. This process occurs in a very fast time frame, maybe 100 femtoseconds. Really quickly after that, sometimes some of these carriers are separated, and that's what's good, and that's what happens in the external circuit for creating photovoltaic. And after this process, there's some bound excitons that can occur. The interesting thing about the terahertz spectroscopy is we can tell the difference between these two states, between charge-separated states and between these bound excitons because of the nature of their photoconductivity. So just to finish, what are the applications? There are applications in imaging, which you probably all know that terahertz is used to look at the foam on the space shuttle external fuel tank before every launch. And people are trying to use imaging in airports to look for shoe bombers and underwear bombers and things like that. But what's interesting here is you've seen this stuff in the news, right? This is really not terahertz. It's really sort of sub-terahertz. It's really hundreds of gigahertz kinds of things. And it's good for imaging. But say this is supposed to be some kind of plastic explosive. In order to determine if this was plastic explosive or bubble gum stuck to the bottom of their shoe, you really need to do spectroscopy over a wide band where you can get some fingerprint information. And here we show where we've looked at some common plastic explosives and show that you can see the difference in the spectra. And this was an example. We didn't do either one of these. This is an example in the literature of somebody doing terahertz from 25 meters, so standoff detection. And what you like to do is couple this kind of imaging with the spectroscopy. That's sort of the goal, the long-range goal. And of course, we're still looking at trying to do some interesting things with organic charge transport materials using that spectroscopy. So there's a poster on this also. That's it. My time's up.